my name is Saoirse Quish and I'll be presenting to you today. In this lab, we investigated the mechanical and degradation properties of a porous polylactic acid log pile scaffold. Solid scaffolds were used as a control in this experiment. The PLA scaffold was developed layer by layer with fusion deposition modeling, FDM, using a computer-aided design. The PLA was used in this lab for the potential bone tissue engineering scaffold as it has good biocompatibility through mimicking the extracellular matrix of damaged bone tissues. It also has good biomechanical properties. Along with the good features that are looked out for using FDM technologies, as PLA is extremely ductile and has a low melting point. The overall objective of this experiment was to design a PLA log pile scaffold using FDM technologies fabricated for the use in bone regeneration, followed by the implementation of examinations to test its efficacy in bone tissue engineering. The method, as you can see here, is in a flow chart. It started out with the first lab, which involved the fabrication of log pile porous scaffolds with Fusion 360. After this, the scaffold was 3D printed, and then the second lab occurred. The second lab involved the uniaxial biomechanical testing of the log pile and control solid scaffolds under compression. Information on the mass and morphology of the scaffolds were obtained pre-degradation using an Olympus microscope. This was followed by a 7-day degradation study of the log pile and solid scaffolds, which occurred in the third lab. This included the immersion of scaffolds into 20 milliliters of NaOH for 7 days at 45 degrees. After these 7 days, they were reweighed and re-examined under the microscope. Images were analysed using image day analysis, which we can see in figure 1 below, to look at the solid and log pile scaffold pore and strut diameter after degradation. So in the results, figure 2 shows the first graph, which expresses the measurement of compressive modulus in the solid and log pile porous scaffold. The mean compressive modulus is higher in the solid scaffold than the log pile porous scaffold. This was an expected result due to the porosity of the log pile scaffold. Normal bone has a compressive modulus between 90 and 209 megapascals. Therefore, this would be a good scaffold as it is even stronger than bone, and bone's most important function is to be strong and hard. Then the second graph in figure 3 depicts the scaffold's mass analysis before and after degradations. It shows the non-degraded solid and degraded solid alongside the log pile degraded and non-degraded scaffold. It is clear that the degraded rate of the log pile scaffold is less than the solid scaffold. Finally, the change in average pore and strut diameters are compared in figure 4. The blue bars denote the scaffolds before degradation, and orange shows after degradation, this pore diameter and strut diameter size. Finally, figure 5 and 6 show how the PLA porous scaffold lost less mass than the solid, therefore is a better material. So here we can see this is the scaffold before degradation and this is the scaffold after degradation. The results of figure 2 are statistically significant as the p-value was less than 0.05. The literature states that PLA has a compressive modulus of 246 megapascals and a porosity of 24.1%. Using the open cell modulus equation, 0.14 GPa compressive modulus was calculated for the log pile scaffold in the literature, which is extremely close to our data of this value, which was 0.16 GPa. Therefore, the test results are verified. The compressive modulus of human trabecular bone is normally 0.15 GPa, therefore this PLA log pile scaffold is suitable to use in bone tissue regeneration as mechanical properties are desirable. Finally, to conclude, our experiments were successful as the PLA log pile scaffold was said to be promising in use of bone tissue engineering. This was shown through verification through the literature of their results and ours, and just from my results in general. Thank you so much for listening, and I'll talk to you again. Bye.